Yeah, sure.
Because you said you want to reproduce the plot in the paper and they have different Fermi levels?
Well, to reproduce qualitatively. It's only qualitatively, yeah. Because because the paper is used a tight binding model, which I'm not sure which one, but anyway, we are a KP, so we are not even close.
So changing number of K points then gives different results. Why?
No, it's just convergence. The more K points, the more precise you are. So at some point it will not change anymore. So we were here. Okay, now I'm running locally, but okay, if you want the figure, where is the figure? If it changes, it just means that we have not enough K points. Go more. Yeah, so I think, but this at least you see it's exactly at -1, so we don't expect it to change much anymore. Okay, maybe it will a little bit, but that's what one should always check in any numerical calculation. So, and the particular Fermi level, yeah, is just arbitrary. We can change the velocity and it will be somewhere different. What will be fixed is that, no, with velocity we don't change. Oh, no, it's exactly from Fermi level. So if we change the Fermi level, actually you can see that no, it is not it's not a function of Fermi, it's a function of omega, right? And this is exactly double Fermi level. I mean displacement of the K point, the Weyl point from the Fermi level, how we say. So when we define two Weyl points, we'll make a block diagonal Hamiltonian. Okay, so basically two Weyl points, but they don't interact. There is no hopping between them. And we all put them together in the gamma point, which doesn't matter. We could also shift them in K space. It would not affect anything because they don't know about each other. But let's keep them just at the gamma point. So one is shifted 20 MeV above, the other shifted 20 MeV below, and we have them with the same magnitude of speed, but you see here we have put different signs. Here we have a minus, here we have a plus. So what we do with this? With the minus sign, we change what? What? Will it change anything? A sign? Yeah, well, the chirality, basically. So, okay, in the same way, we run the calculation. Where are we? We've done this. Okay, and now we can plot this. Okay, again, Berri curvature. Not the best plot, but okay, let's put it some. We can tweak it a little bit. Minus 0.0. Okay, let's stretch it a little bit. Wait, why did it happen this way? Why did it change this way? I don't know. No, I think 0.2. Okay, too much. Okay, so on one Weyl point you see the upper band is blue, the other band is red, and the other is vice versa. So it's two Weyl points with different chirality. This crossing, you shouldn't look at it because it's not an actual, I mean, the Weyl point, the 2 points don't know about each other, the Hamiltonian is block diagonal, so yeah, technically it is a crossing, but it doesn't give any contribution to anything. Again, we could instead of these put them at different K, and the crossing will be somewhere there, far from Fermi level. It wouldn't affect, but it doesn't matter. So now we calculate for a set of Fermi level. Yeah. Basically, first Fermi level passes through the lower value point, the last through the upper, and we have in between. So yeah, we can calculate this. What I forgot? Okay, there is a typo. It should be system 2Y. Yeah, corrected, because if you have run the previous cells, you will do the calculation for the one point system and be surprised why it is the same. Correct this typo. I got an error because I reopened the notebook and I don't have this system while defined anymore. So now should run. Yeah, calculating the same CPG. Yeah, that will take some time. Yeah, and after we finish the calculation, okay, let's plot it. Okay, let's plot for. Okay, the more time it takes, but I think okay, you see, it's now calculating 100 by 100 by 100, which is the last one. Okay. Yeah, so first plot, what it is. So with this we have chosen the first Fermi level, right, and for all frequencies. And just to check the convergence again. So I think the last one is, okay, the 100 is this dark red and the purple. You see, they are not much different, the last two. Yeah, 80 and 100, we are more or less converged. Yeah, and we have this at plateau at -1. Good, so, okay, we don't care about what happens for little k points. Let's plot everything for 100, but for different Fermi levels. So that's what we get. So is it similar to what Adolfo obtained? Well, qualitatively. Yeah, so this line, when the Fermi level is exactly between the value points. You see it is 0, and we also got a 0. Good. And yeah, so if for smaller Fermi level, we have a more narrow plateau, but we still have this plateau. Yeah, and of course, maybe this is more shallow just because we have a higher smearing. So basically, that's it for the KP. Any questions on this? No? Quite clear. So we can go to the. Sure.
This object result that we
Uh-huh.
have. What properties? It's an object that is user defined, but what properties does it have?
Well, it's defined here in the code. Well, quite many. You can check. Okay, let's. What doc? Sorry, docs. Okay, we can. Result. Okay, did we document it? We are not fully result, but so basically, what is returned is a result, something called result dict, so a dictionary of results. So then you pick up one of them, which are labeled by your tabulators And each of them has, and we have, yeah, our documentation is not exhaustive. So, but, okay, so then you need to go to source code. Well, the simplest thing is, say you have this result after you go. Okay, result and key. Okay, this is just a dictionary, yeah, labeled by the number of key points. Or okay, for now you can put a dot and press a tab, and actually it gives you all possible. But basically, okay, what is important for us is the results, and basically, okay, it's a dictionary labeled by the calculator. So that's what we need. Basically, so what we, for example, comment what it is. Okay, undocumented. It's because we didn't document it. It's a user-defined calculator. Okay, so for example, first of course, the data. That's what you need is this array, like for every frequency, every Fermi level, and yeah, only this, right? And Cartesian components if they are present. So what it is also has. Okay, rank, it's just the dimension of the tensor, so it's 0 dimensional, it's a scalar. And many other things. So energies, so basically shows the Fermi levels and the frequencies for which it was calculated. What else? EE titles, so the titles of the energies. Yeah, so the first is Fermi level, the second is omega. So, and, well, basically all information, I hope everything that is needed. Then, okay, it has a properties like multiplication to something, number of energies to number of Fermi levels, I guess. Yeah, there is also a data smooth, but for that I think you need to define a smoother. I think they are just the same as the data, if we didn't define any smoothing. Yeah. Uh-huh.
When you write the run command, then can you please at least briefly say the results that are printed, what do they mean?
Sorry, what?
The WannierBerri.run command?
WannierBerri.run? What it prints?
What it prints, yes.
Yeah, I don't know how much it is informative. But, okay, so, okay, we have chosen this print key points false, is just to make the printing shorter. So, well, basically, so the grid, so it says, okay, that's from the grid, from the run, it was, I think, well, basically it says that we are running this and done in, like if the execution takes a long time, it also says, okay, we did 10 key points, 20, like 50%. We estimated time, but because here it's quite fast, we skip this printing. So it says, okay, the grid that it was the full grid 100 by 100, okay, FFT is 10 by 10, then NKD, basically it's the ratio of two grids. Then these big K points, it's big K points is the full FFT grid. So it's not one K point, it's in this case 10 by 10 by 10, which is repeatedly. So on every step, we create this FFT grid, we Fourier transform everything what is needed on this K grid, which is this regular grid, but shifted by a small vector. So by this shift, we recover the full grid. So we process all the K points on this grid, all in the one shot, say, for more efficiency. In
this sum of weights, if our calculation is wrong, this sum of weights, we should check it if it's always one.
Nothing you can do about it, and I mean, unless you change the code, I don't think it can become not one. To be honest, it's mostly for when you develop a code, especially these routines which change the behavior with the k points. Yeah.
I did not change the code, and my value is 476.
Huh? Sum of weights?
Yeah.
176.
476.
476. In which run? When you tabulate it or? But it was for integration or maybe for interpolation. When you just plot a long line, maybe it's...
Maybe I'm looking at the result of...
Yeah, when you tabulate, actually, the weights are not important because when you work on a path, so you're not summing them. So maybe it is there. Yeah, it is equal to the number of your k points. Yeah, it doesn't matter. In that case, yeah, it's irrelevant. Yeah, so were there questions? No? Not anymore? Okay, so the tight binding. Basically all the same, just let's build some simple tight binding model. Okay, again, start, all imports, check, okay, parallel, okay. Haldane model. I think you heard about it maybe during these lectures. Basically a honeycomb model like graphene, but it has this complex nearest neighbors. We are using the module called PSTB, which was developed by David Vanderbilt and Sinisa Koch. So it's just one of the convenient quite popular ways of defining a tight binding model. And inside, in principle, it also has some methods to evaluate different topological properties. But here we just use it as a way of writing a tight binding model, just as a format. And so we set the hoppings between different places. So between different sites, so we have only two sites. On the two sides of the honeycomb lattice, they have different on-site energies, minus delta and delta. This is to break the inversion symmetry, and then with these complex hoppings, next nearest neighbors, which break the time reversal. So yeah, to have some anomalous hole, we need to break time reversal. No other way. So yeah, so we define a function, and for some set of parameters, we create this model, which is an object of PSTB, and now there is an interface how to transform this object of PSTB to the system of WannierBerri. And from this point, it works in the same way as it would work for Wannier functions, almost the same way as it works for KP. But okay, KP has this difference that we have this artificial box. Here, the unit cell is quite natural. Have a periodic system. So we define such a weird path. Here, one known means that we have a break. We don't interpolate between gamma and K1. And I go through the border of the Brillouin zone just to check the symmetries. So it's just to see what is the symmetry of our system. So far we didn't specify anything. So we didn't specify any symmetry. So what symmetries does our system have? What do you think from this plot? Does it have inversion symmetry? No. Let's see. If it has inversion, it can. Okay, this is the Brillouin zone. So let's say this is K1, K2, K3, K4, K5, K6. If it has it, then K1 and K4 should have the same energy. It doesn't. Okay, there is no. Yeah, that's exactly because in our honeycomb lattice we said plus delta and minus delta, yeah, for the site energies. So if we had inversion or time reversal, it will no time reversal not inversion would interchange the sites, and the on-site energy would be the same. So yeah, we broke inversion. We can restore it actually, so, but we will not, because we will calculate shift current later. So, but first let's calculate the anomalous Hall. Okay, what else can you calculate for the Haldane model? Okay, just defining the standard density of states and anomalous Hall conductivity calculators. Again, we use tetrahedron method. We exclude the external terms. Yeah, we run. We don't need too many K points because that's Fermi C with tetrahedron should be good. So okay, the density of states looks like this. Yeah, interesting that we have such peaks at some points. But okay. Yeah, and that's the anomalous Hall conductivity. So we see that if the energy is in the gap, we have a plateau. So that's the conductivity, but that's the 3D conductivity. So it calculates for something for 3D, so it's in Zeeman per meter units. What we need is actually the 2D conductivity is in Zeeman. So sorry, not Zeeman, Siemens. Okay. Siemens, not Zeeman, sorry. Okay, so what we need to multiply it by the lattice vector in the z direction, which is arbitrary, but we have set it to something, all right? And we have set it actually to 1 angstrom. And we get some value of conductivity. If we check what is the conductance quantum, it's just the same. Oh, sorry, half conductance, half one. So we took from there is a modulus psi pi constants, which has a variable physical constants, has all the physical constants. So we take it, divide by 2, and the unit. So great, we found that it has a quantized Hall effect. Great. So with some change of parameters, we can change it to a non-topological phase. So you can play with parameters of the model. Okay, the simplest way to get rid of the topological phase is just to remove this phase. So yesterday I saw a poster by someone here. Are you here? Yeah. So, and I saw this figure. So can we reproduce it? Okay. We already have a calculator for shift current. It is there. We don't need to redefine it. So let's define two systems. Okay, this is just identical to what we have, and here we multiply the phase to 0. Basically, what it means that we don't have any phase. We don't break time reversal, so we cannot have any anomalous Hall conductivity. But it's okay. We don't want it. We want to see what happens with shift current. What did we get? Okay, that's all in one cell. So let's see what we run for. Okay, first we just, for this trivial model, we plot the bands just to see how they look like. And then for the trivial and the topological phases, we do the calculation with the same calculators. Okay, and we have plotted. Okay, we have this plot, so that's the band structure. That is anomalous hole. You see in trivial phase, I wonder what parameters we need to choose to have some breaking of time reversal, but still, and the gap, but still some anomalous hole. It's just a matter of playing with parameters, I guess, to find. But okay, let's play with this most simple case. Just the density of states, and okay, they have different magnitude of the gap, but let's pick a Fermi level somewhere here that both of them are gapped. Okay, then let's calculate the shift current for here, just for convenience. Of course, we could set different Fermi levels, but okay, we have a calculated shift current, so there is a parameter SC eta. Well, it's just another smearing parameter which is needed for calculation. We set it quite big, but just to converge faster. Okay, take the grid, not very dense, again, 20 by 20. Okay, but this model it's not a, you have seen that while node is really a problem. And in ab initio calculations, it's even more a problem. There are a lot of while points, a lot of line nodes or quasi-line nodes, which for problems are the same problematic, actually. Here we don't need too much, and we run it. So, okay, it's not, again, no problem. That's what we get. Well, of course, probably 20 by 20 is not too much, but there is some qualitative difference, no? Where was the photo from the poster? Somehow. I don't have exact parameters, so, and of course we didn't converge, so you can take a bigger grid, maybe it will look a bit better. Where do we do it? Okay, let's do it like this. Did it finish? Oh, a little bit different. Okay, of course, changing parameters. What is topological, what is trivial, it's a different model. So that's okay. Just examples that you can calculate also shift current. And the last thing, maybe that how to write calculators. We have a template which is called a product. And for instance, let's say we want to evaluate this tensor. Why we want to evaluate it is another question. But assume that you had a theory from which some transport coefficient has this integral. And for this, we already have. So again, we need to define a formula, which is the matrix element. Okay, let's call it my crazy formula. We already have implemented Berri curvature, which is called omega. Orbital moment, we also have it. And we have this inverse effective mass, tensor. Derivative of energy with respect to 2k vectors, which will be a
I think we don't have, does everybody have this?
No. Really? So your notebook ends just with this? Yeah. When did you? Oh, wait. When did you download? When? Huh?
Just before the.
Wait, I think I also. No, I'm pretty sure that I was doing it on another computer, and here I downloaded it from GitHub. But okay, let's check. And I didn't update them today. So, okay, what am I missing? Tutorial timeline. Oh, really? Okay. So I did it on this computer. It's a local change. Okay, okay, a lot of. Now. How many files? Okay, I didn't clean. Usually, before I push to the GitHub, I clean. Sorry, it's okay, I got it. I didn't merge it. It was on another branch. Okay, there is a second. It was on the develop branch. Okay, you can switch, if you go to GitHub, you can switch to the develop branch and look at the tutorial tight binding. It's here. Okay, now, because usually before I push, I clean everything, but now I didn't. But anyway, so basically that's all what you need. Just copy, you can copy paste this. It's only one thing. Sorry. Yeah, so how you define this product? You just say, okay, I want the product. Okay, there is a called formula product. So basically, you give all these previous formulae as a list, and it knows what to do. You can give it some name, which may be never used anywhere, but just for a label. And then a calculator, and you define which derivative of the Fermi distribution you want to use as a weight. So in this case, we have Fermi C, so it's the first derivative. So you can, so zeroth derivative, no derivative. So if you had F prime, so you put it 1 or 2. And that's it. So we can do the calculation and check. Yeah, and you see we can also use a tetrahedron method, which is calculated for all static calculators. Static means it doesn't depend on any omega. Just with omega, it's a little bit, this integral in a tetrahedron is a little bit more complex. So far not implemented, but there is no principal difficulty. But you see the advantage that when it is done as in the object-oriented paradigm, so you implement it once and then you can use it for everything. So you just inherit the class and it uses all that the parent had. Okay, so we evaluated something. Okay, we don't know the physical meaning of this curve, but whenever you know a physical meaning of something, you can calculate it. For example, there was a question about anomalous neurons' conductivity. Basically, to calculate anomalous neurons' conductivity, first you need to evaluate an integral of Berri curve. Okay, for anomalous hole, so that's AHC, you integrate the Berri curve, which is F, for A. Anomalous neurons, which is a thermal effect. Yeah, you just calculate omega with F prime, for example. Well, how can you calculate it? First, obvious, you just take the HC calculator as a curve in Fermi levels and take a derivative. It's the simplest. But for example, let's calculate. So again, okay, let's.
At t equals 0, though.
Huh?
At t equals 0 is not h to calculate it, right?
Yes. So yeah, the best is calculate first. No, of course, it's not a final quantity for the anomalous neurons. It's something which you use. So then you, I don't remember, but there is a, basically there is some function of some logarithm of f or minus 1 plus or something. I don't remember. You can look at the papers. But basically, that's the quantity that you need from which you can evaluate anomalous nerves. Of course, the intrinsic, the Berry curvature contribution, but you can calculate it at every temperature for any Fermi level, for whatever. So once for all, you just calculate this quantity. And then you will do it. So question, how to calculate this thing? Because after that, it's just taking a one-dimensional integral in Fermi levels. It's okay. Let's copy. Wait. Wait. Shit. Yes, how do we do it? Okay, we don't need any extra formula because, okay, the matrix element is just the Berry curvature, which we already have. Wait. Yeah. So let's call it A and C. So anything else that we need to change? Basically, that's all. We can also add some factor, but okay, we will not. A and C, A and C. So then, yeah, and we use the topological, otherwise. Okay, let's calculate them all because and AHC is the same thing. AHC, okay, it should be. Of course, it's. It's like this, right? What did I do? Key error on my card. Wait. Okay. So, okay, let's cut this. Okay, just like that. Okay, now let's plot. So let's plot A and C. What? Okay. Of course. It is just a vector, so we don't need this. We need only this. It's okay. Okay. You can also, if you want, you can plot. Okay, let's make it a line. AAHC. Oh, okay. Yeah. Okay. So the upper is the minus derivative of the lower. Oh, that's it. Okay, any questions, suggestions? Yeah.
Educational.
Mm-hmm.
I think it's not possible in KDP, but I want to make sure. Is it possible to see Fermi arcs?
Fermi arcs? It's not a WannierBerri thing because to do Fermi arcs, what you do, you make you need to either semi-infinite with green functions or a slab. Yeah, so well, in general, WannierBerri is optimized to use with a relatively small unit cell and many k points. So when you use supercells, slabs, you are in the opposite limit. So yeah, so Wannier tools does all this, and yeah, formally you can do this. I mean, implement the same in WannierBerri, but like it will not. Well, of course, let's say if you calculate, if you make a slab, yeah, and write it as a tight binding model of a slab, full slab, then you can plug it in WannierBerri in principle and plot the 2D band structure. So yeah, that you can do if you want. I don't know.
Can I suggest something?
Huh?
So
Sure.
What you can do is what Stepan said. So you construct the slab, you start with the 3D, construct the slab, and then you plot the density of states at the surface. And then you will see the formula.
Yes, you can. So for that, you need to define a calculator which projects density of states only on the surface layers or something like that. Yeah. You can do that. But again, it will be a slab. It will not be semi-infinite. But okay, if it's okay for you. Anything else?
I have a question.
Yeah.
So let's say that you wanted to use another one-dimensional quantity.
Another?
For example, instead of the Verilog vector,
Yeah.
you wanted to use, I don't know, some electric field Verilog vector.
Wow.
Quantum methods, for example.
Yeah.
Could you be able to modify the one code in the WannierBerri?
Well, you can do it if we already have all the needed real space matrix elements, yeah, right? So we have position matrix elements, and we have Hamiltonian spin matrix elements, and depending on quantity, you need different the matrix elements between Wannier functions. So if all the needed are already there, then in principle you can again write your own calculator which takes it. If they are not there, okay, you need to somehow implement it inside. But somehow, yeah. Well, in principle, yes. If it's any property which is a property of the ground state of electrons in this unit cell, in principle, anything can be implemented. So, then, let's thank me again. Okay, thank you for coming, actually.